Hey guys, in this video I'm going to go over the questions from the 1.5 through 1.8 homework. In the first question we have a function f that's given to us in the form of a graph, and we are evaluating the limit as x approaches -1 of a composition of itself. And let's go over the steps for how one can do that. So first of all, we're going to evaluate the limit given, so as x approaches -1 of the inside function. And like we've kind of talked about in class, whenever it's a composition, you're going to have to take note on if it's coming from above or below. This is what I mean by that. So here's -1, and as the limit as x approaches f of x of -1, you can see that it's going to be 2 from both sides, and so it's going to be equal to 2 for sure. So we know that it's going to be 2, but also note that it's coming from 2 from below the graph. So I'm going to make a note of that, from below, and to denote that I'm going to put this superscript of that negative, which means that in my next limit, so as I evaluate the limit of the outside function, I'm going to evaluate it from this value right here. So I'm going to evaluate the outside function as x approaches 2 from the left of f of x. And so if I do that right here, so here's 2 of f of x right here, and we're going to approach 2 from the left side, and that's going to be equal to, you can see that as 5. And there you go. We have our limit evaluated. Okay, number 2, likewise. So we're going to evaluate the same thing. So we have the function f. We're going to evaluate the limit as x approaches -1. Start by evaluating the limit of the inside function. So the limit as x approaches -1 from the left. So it is approaching 3. Just approaching -1. So as it approaches -1, it's going to be 3 from below. Okay, and so I'm going to evaluate the limit as x approaches 3 from the left of f of x. And so going here, the limit as x approaches 3 from the left side is -1. So that's going to be -1. So that's going to be C. Okay, moving on to 3. So we have a system of equations, we have a piecewise function. So let f be a piecewise function as defined. The value of the limit as x approaches 2 from the right of f of x is. So imagine we had all 3 of these pieces right here. So from the left side we have a linear function. It has a y-intercept of -3. So it's got a slope of 5, so it's probably going to look something like that right there. But we're only drawing it to less than 2. So it'd probably look more like this right here, maybe something like that. And then it's going to be 9 at x equals 2, So it's going to go up like that. And then it's going to be 9. And then it's going to be 4x plus 3. 4x plus 3 there. So I'm not really sure if this right here and this right here are at the same spot essentially. Okay, but what we're trying to do is we're trying to evaluate the limit from the right side. So where is this going to be? So pretty much the only piece that matters is this one right here. This one's the only piece that matters. And so I can basically just substitute this value right here into this function, and I should get its limit. Doesn't matter that right here that x is defined at 2 as 9, because I just want to know where this is going from the right side at 2. So I should be able to figure that out just by plugging that in right there. So 4 times by 2 plus 3, that's going to be equal to 8 plus 3, which is going to be equal to 11. Okay, so there you go. I'm also just noticing that my graph that I drew, I was doing at -2, but it definitely was at +2. So sorry, I wasn't really paying attention. But in any case, should be 11. Okay, Hopefully that makes sense. This is the only part that matters because I'm evaluating 2 from the right. Okay. Question 4. It looks like we have some values of the functions given to us as well as their limits at x equals 2. The table above gives selected values of limits in the functions f, g, and h. What is the limit as x approaches 2 of this right here? So it looks like we're going to use our property limit properties. Okay. So essentially what I can do with my limit properties is this right here. So I can write this as the limit as x approaches 2 of h of x times by, I'll just use parentheses, the limit as x approaches, I'm going to put that 5 like this right here. So I'm going to write it as 5 times by the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. And we have all these values in this table given here, so let's go ahead and evaluate. So the limit as x approaches 2 of h of x is 2. So I'm going to put 2 right there. 5 times by the limit as x approaches 2 of f of x, which is going to be 4, plus the limit as x approaches 2 of g of x, which is going to be -6. And so we have 2 times by 10 minus 6, which is going to be equal to 2 times by 4, which is going to be equal to 8. And I definitely messed up somewhere. That's where I messed up. 1 second. I know my times tables. That's going to be 2 times by 20. For some reason I was multiplying those together and not those together. So 2 times by 20 minus 6. There we go. So that's going to be 2 times by 14, which is going to be equal to 28. And so C will be the correct answer there. Okay, looks like C is just going to be the correct answer. I'm just kind of noticing that. Let's go on to the next one. All right, so if f is the function defined by f of x is equal to this given expression, find the limit as x approaches 2. So to note here, let's see if we can use substitution. So if I can substitute this in, which probably not going to happen, so let's look by substituting it in. That becomes 4, right? Plus 2 minus 6, that's going to be equal to 0. So 0 is going to be my denominator. That doesn't work. So probably what's happening is that they're trying to get you to simplify this expression so that after I simplify, I can plug in 2. And so if you take a look at the numerator there, the numerator can be factored into x plus 2 and x minus 2 over, and then I can factor this one. So what multiplies to be -6 and add to be +2? I'm going to say what multiply, oh, sorry, I was looking right there. What multiplies to be -6 and adds to be 1? So that, I think that's going to be +3 and -2. Those can cancel. Okay, so then f of x is equal to x plus 2 over x plus 3. So remember what we said, that if there's a factor on the numerator that's also the same as a factor on the denominator, that causes a hole in this function at x equals 2, which is why I can't plug it in here. But I can plug it in here, and that will give me what the output would be if there wasn't a hole there. So then if I plug in 2 here, I can do that. So that's going to be 4 over 5. So that's what the function would be if that hole wasn't there. But that's what the limit is going to be then. So the limit is going to be 4/5. Also C. So all right, for 6. Okay, so for this one right here, we have some, looks like we got some trigonomic expressions. I'm probably going to do this one here, 1 second. So that I have more space, I'm going to do this on another page. Okay. So it is known that the limit as x approaches 0 of sine of 2x over 2x is equal to 1. Okay, so we have this value, this limit of this function given here. So what is the limit of this expression as x approaches 0? So basically what they're trying to get you to do is to simplify this and get this out of that so you can use that. Because the problem with this right here is I can't plug in 0. If I plug in 0, especially into this part right here, I get 0 on the denominator, which is not good. Okay, so let's see if I can simplify it to a point where something can cancel and then I can substitute. So let's think about tangent of x. So tangent of 2x, tangent of 2x is equal to, it's the same thing as sine of 2x over cosine of 2x. Okay, and secant of 3x is equal to 1 over sine of 3x. So we're going to probably want to use these. And so let's go ahead and see if I can do that and simplify. And look right there, I do have a sine of 2x on the numerator. So somehow I want a sine of 2x to be, or a 2x to be underneath that. So also notice that 6x is the same thing. I'll put this up here. 6x is the same thing as 3 times by 2x. So imagine if there's a way that I can get this to be underneath the sine of 2x. Well, then I can use this right here, right? Okay, so I have the limit as x approaches 0. I'm going to write this as sine of 2x over cosine of 2x over 6x times by 1 over sine of 3x. So that's because we're doing 6x times by what this is also. I'm going to just like put this 6x in the numerator there. So I'm going to write it like 6x over sine of 3x, if that makes sense. And I'm going to do a keep, change, and flip. So then this is going to be equal to the limit as x approaches 0 of sine of 2x over cosine of 2x times by, I'm going to flip that one, so it's going to be sine of 3x over, now instead of writing 6x, I'm going to write 3 times by 2x. Okay, because now I'm going to rearrange some orders because this is all being multiplied and divide, so I can rearrange them because they're commutative, right? And so instead of putting cosine over here, because these are being multiplied, and I can always multiply I can multiply numerators and I can multiply denominators, I'm going to move this over here. I'm going to put the 2x over here. So I have the limit as x approaches 0 of sine of 2x over 2x, okay, times by sine of 3x over 3 times by cosine of 2x. Now I can apply the properties, so I can split everything up the way that I want it to, right? So the limit as x approaches 0 of sine of 2x over 2x times by the limit as x approaches 0 of, I'm going to do 1 over 3. So this right here is the same thing as if I were to multiply by 1 over 3, right? So if I do that, I can evaluate that limit separately. And then times by the limit as x approaches 0 of sine of 3x over cosine of 2x. Well, here, I know what this value is. Excuse me, that value is 1, right? This value right here is going to be 1/3. And then this value right here, well, there's not a problem with plugging in 0 right here. I can use substitution because I won't get 0 in the denominator. If I plug in 0, this becomes cosine of 0. And cosine of 0 is 1, right? So this will be equal to, we'll say over 1. And if I plug in 0 here, I get sine of 0. And sine of 0, it's going to be 0. Now that's not making a whole lot of sense. So let me think about what I did wrong. So cosine, secant, that's what I did wrong. All the way back there. Secant, I wish you guys were here to tell me this ahead of time, like in class, so you guys can tell me when I'm doing something wrong. Secant is not 1 over sine, it's 1 over cosine. 1 over cosine. So notice that for all these values where I put sine of 3x, sine of 3x, sine of 3x, that's not sine of 3x, that's cosine of 3x. Okay, so cosine of 3x and there we go, that's making sense, because otherwise I knew something was wrong, because otherwise our values, it would have been 0 in a, yeah, that was 0. That just didn't seem right to me for it to all be 0. In any case, maybe it was right, but I hope it's not. In any case, so cosine, that's going to be cosine of 0 divided by cosine of 0, and in either case, cosine of 0 is going to be 1. And so now we have all of this right here, that's going to be multiplied, that's going to be 1/3. Okay? So 1/3 should be our answer right there. Okay. So going back to 7, 7's going to be very similar. I'll just kind of let you know what you should keep in mind. So cosine, I don't know if you actually have to change this one right here, but for cotangent, so cotangent of 2x, that's the same thing as, let me make sure I got this right, as cosine of 2x over sine of 2x. Okay? I think that's correct. And I don't think you have to change this one. I can't imagine you wanting to change this one. But in any case, you're going to want to use that. Also keep in mind that 8x is obviously the same thing as 4 times by 2x. So it's going to be very similar. Try and do something very similar to what I just did here. You're trying to get this out of that right there. And then you can use some properties. Okay. Question number 8. So the limit as x approaches 3. I can't just plug this in. If I plug that in right there, that's going to be 27 minus 27, so that's not going to work. So let's see if I can simplify this. So x minus 3 over x cubed minus 9x, I can factor an x from the denominator, and then I can also use the difference of squares, because then that's going to be x plus x squared minus 9, so x plus 3 and x minus 3, right? So those can cancel. So there I know that there was a hole there, 1 over x times by x minus 3, and now I can substitute 3. Can I substitute? Goodness sakes, my math is being so bad right now, guys. Plus. This is why I need you guys here. Now I can plug in 3 in here, because plugging in 3 here would be the same thing as evaluating the limit as 3 approaches this right here, but I don't get any errors here. So then that's going to be, so this limit as x approaches 3 of x minus 3 over x cubed minus 9x is going to be equal to, if I plug in 3 right there, it's going to be 1 over 3 times by 6, which is 1 over 18, which will be B. Okay, should be good there. Let's look at, did I circle this one? Sorry, 1/3. Okay, let's go to 9. We have another piecewise function. So if f is the function defined above, then the limit as x approaches 1 of f of x is. So I'm going to probably need more room than what I'm given here. So let me go ahead and copy this down. Okay, so if f is the function defined above, then the limit as x approaches 1. So if I'm taking a look at this function, the function, this is pretty much the function for pretty much the entire domain, except at x equals 2, where it's going to be something different, right? Sorry, at x equals 1, it's going to be something different. It's going to be 2 at that point. So, little trick here that I always tell people is that whenever you have an absolute value function in your graph, you can always split the piecewise function, or you can always make that into a piecewise function, because, well, let's go to Desmos. So if we have the absolute value of x, absolute value of x minus 1. So x minus 1. Okay, so this is the graph of the absolute value of x minus 1. Now this in and of itself is a piecewise function too. It's the function of negative x plus 1 and x minus 1. So I often like to just do that. So x minus 1, the absolute value of it, is also just a piecewise function. So it's going to be negative x minus 1 for x is less than 1, and it's going to be x minus 1 for values x is greater than 1. And again, that's just kind of like, you can look at this right here and see that that's the case, right? So if that's the case, let's go ahead and I'm going to split this up even more. I'm going to add to it. Okay, so I'm going to say that f of x is equal to, so to the left of 1, it's going to be equal to, so x minus 1 squared and x plus 1 over negative x minus 1. So notice here that I'm not writing the absolute value because I'm going to write this in two parts. It's going to be negative x minus 1 when x is less than 1. And it's going to be 2 when x is equal to 1. And then it's going to be x minus 1 squared times by x plus 1 over just x minus 1 when x is greater than 1. So notice here I'm breaking this into two different functions according to, because this is a piecewise function as well. Okay, so then the function f is defined above. We're trying to find the limit as x approaches 1. So how do I evaluate the limit as x approaches 1? So I'm going to evaluate it from the left here and from the right here. So as I notice I can also cancel those out right here. So those will cancel. So let's say I evaluate the limit as x approaches 1 from the left. That means I'm going to do it from this side right here. Well, again, if I cancel out those factors, I'm going to have x minus 1 times by x plus 1, and then there was a negative left over in the denominator, which just means that that's going to be negative right there. Okay, so I can plug in 1 now because I couldn't plug in 1 before because that would make that 0, correct? So if I plug in 1 here, I get 1 minus 1, that's just going to be 0. So this whole thing is just going to be 0. If I evaluate the limit as x approaches 1 from the right, well, remember, I'm going to evaluate this side. Those are going to cancel. So I'm just going to have x minus 1 times by x plus 1. Okay, and if I plug in 1, because I can now, because that's not a problem in the denominator, this becomes 0, that becomes 2. In either case, when I multiply those together, I'm going to get 0. And so from the left and from the right, it's the same. It's going to be 0. So the value, the answer should be 0. Okay, that's a fun one. 0. If f is the function defined by f of x equals this expression right here, what is the limit? So I think we can't plug in 1. We can't use substitution just yet because that would give us 1 minus 1, which would be 0. But we do have square root of x minus 1, and if you see something like that, you're going to multiply the top and the bottom by its conjugate. So we're going to take f of x, and that's going to be equal to x squared minus 1 over square root of x minus 1. We're going to multiply top and bottom by the conjugate. Okay, so that's going to be equal to, I'm just going to leave I'm actually going to factor that. So that's going to be x plus 1, x minus 1 times by the square root of x plus 1 all over. Now when I FOIL this out right here, I don't want to FOIL this out. I do want to FOIL this out because that's going to become x right there. The middle terms are going to cancel, and then that's going to become minus 1. And so because I've done that, these factors will cancel, which now gets rid of, which basically, I guess you can say, kind of caused a hole, and that was a problem for us. So we have x plus 1 times by a square root of x plus 1. So I can substitute 1 into this right here, and this is the same thing as this right here, but we don't have any problems with our domain, right? And so with that being said, if I plug in 1 for here, I'm going to get 2 plus 2, which is going to be equal to 4. There you go. Okay, so for 11, looks like here I can already tell we're looking to use the squeeze theorem. So let g and h be functions defined by g of x equals that right there, h of x equals that right there, and satisfies g of x is sandwiched between f of x. Okay, for this interval right here, what is the limit as x approaches 1? Okay, so if we remember the squeeze theorem, what we're basically trying to show is that the limit as x approaches 1 of g of x, okay, is supposed to be equal to, we'll say L. And the limit here, so the limit as x approaches 1 of h of x here will equal L. If that's the case right here, and this inequality is true for this right here, well, then the limit of this function right here, which is what we're trying to find, has no choice but to be the same as these ones right here, because we've sandwiched them. We've pretty much sandwiched that in between g and h. Okay, so that's what we're trying to prove. So all we need to do is show this one and this one right here, and we'll have our answer for f. So let's evaluate I'm going to erase this so that I have a little bit more room. So we're going to evaluate the limit as x approaches 1 of g of x. Okay, so here's g of x right here. Let's see if I can solve it just by substitution, because there's no domain restrictions here. Sine doesn't have any domain restrictions, neither does 4. So substitution should be just fine. So if I plug in 1, I get sine of pi halves, and sine of pi halves is 1. So 1 plus 4, this is going to be equal to 5. Okay, now let's do the limit of our other one. So the limit as x approaches 1 of h of x. So let's go over here. So if I plug in 1 into these spots right here, that's going to be negative 1/4, because 1 cubed is 1. If I plug in 1 to the next one, that's going to be plus 3/4. And then instead of writing 9/2, I'm going to write that as 18/4, because they are the same, but we have a common denominator now. So then that's going to be equal to 18 plus 3, which is 21, minus 1, which is 20. So 20 over 4, which is equal to 5. So I've established that the limit as x approaches 1 of this function is 5, and for this function is also 5. Therefore, the limit of this expression has to be 5 as well, because we've sandwiched it between and within this interval anyways, so has to be that as well. All right, so for 12, it's just the same idea. We're gonna do the same exact thing. We're going to evaluate the limit as x approaches -1 of g of x. So let's go to g of x. If I plug in -1 here, so -1 squared is 1, but it's going to be negative, so that's -1. Plug in -1 there, that's going to be plus 2 plus 3. So then that's going to be 4, I believe. And then I have the limit as x approaches -1 of h of x. Let's see if we get the same thing. So for h of x, if I plug in -1 there, that should be positive 1/2. If I plug in -1 there, that's going to be -1. I'm going to call it -2 over 2, so that I have a common denominator with everything else, plus 13 over 2. So then I'm going to have 13 plus 1, that's going to be 14, minus 2, so that's going to be 12 over 2, which is going to be equal to 6. Okay, so the limit from the left side, or sorry, not from the left side, the limit of this function is 4 at -1, but it's 6 here. So what is the limit as x approaches -1 of f of x? I simply don't have the information. Could I find it? Sure, but not using the squeeze theorem, because I'm not getting anything definitive here. Okay, so cannot determine with the information given here. Okay, let's try 13. So for 13, I think we're also pretty much just trying to use the squeeze theorem. So let f and g and h be the functions defined given there. All of the following inequalities are true for the given interval. Which of the inequalities can be used with the squeeze theorem to find the limit? Okay, so essentially what you're trying to do here is see if you can use the squeeze theorem. So what you want to do is evaluate the limit for all of these right here and basically see if this side will be equivalent to that side. So therefore, the limit of these middle functions has to be the same as these ones right here. So like for 1, for example, so we'll try the limit as x approaches, what value are we looking at? The limit as x approaches 0. So the limit as x approaches 0 of 1/4, well that's going to be 1/4, is going to be less than or equal to the limit as x approaches 0 of f of x. Is going to be less than or equal to the limit as x approaches 0 of x squared plus 1/2. So we know that this limit right here is 1/4. Has to be less than or equal to the limit as x approaches 0 of f of x. Has to be less than or equal to, I can evaluate this limit through substitution, that's going to be 1/2. So here they are not the same, so that means I cannot use the squeeze theorem. This is inconclusive, so conclusive by squeeze theorem. So I can't use 1, right? And what we're trying to find is which of the inequalities can be used. Okay, so definitely not 1. Okay, so I know that so it's probably going to be, so it can't be this one. Also can't be this one since we already ruled out 1. So it looks like it can be B or D. So you have to check if you can use the squeeze theorem on 2 and 3 using the same exact method I did here. So I'll leave that to you guys. Evaluate the limits from these sides right here. Make sure that they can be the same and that they exist. If they don't exist, then you can't use the squeeze theorem either, okay? All right, so hopefully that helped you on this homework assignment.